sort of an idea of how I want to do this. We'll go through the math a little bit.
Wait, I'll go first if you want to do math.
What do you mean?
Because I don't do the math and then we get to the math later.
Can I ask questions? Hard questions? Okay, I'm just joking.
Yes.
Is that okay? Because how deep is your math?
Not very deep. So essentially, what I want to cover is how we model a neural network, feed it an input, what happens to the input, and based on what happens, how do we change things within the network? And essentially, why do we need neural networks at all? Is what I want to cover. I have a sort of idea for it.
Okay, good. Yeah.
Okay.
And you're doing what?
I want to like talk how you can change the parameter by reducing the to reduce the loss and then derive the math from that.
Okay.
Is it?
I like. Go ahead.
What do you think?
I think we have 50 minutes, a lot of time.
So you're saying, how do we derive the math to change the parameter? So I can get to that point and then you can take over.
Wait, I thought you were talking about math.
No, I want to. So my main goal
No.
for this
Okay, everybody-
yeah, that's fine.
is-
Yeah.
intuition.
Yeah.
You know, you have to make sure you understand every single
Yes.
thing here.
Okay.
Maths,
Okay, that's great.
Ready?
Like the idea. Of
Yes.
it. Okay.
their aim is to make sure that you understand the perceptron and the basics solid, at least for intuition, and then you can go on your own if you want to go further. And then I can just say next week, let's code and do something.
Yeah.
Right? Because I want to accelerate this summer. I do not want to waste time.
So my idea is we're going to be building intuition based on reasoning and vocabulary. So I'm going to introduce some terms as we go along, and I'm going to explain to you what those terms mean, and I'll write all those new terms here, just so we can refer back to it. Right? So we initially looked at, I think last week, was if you have a set of data about something, how can you create a model that predicts something else, right? So let's get some context. We have a goal. There's a problem statement that someone is presented. You are being hired by a pet store, right? And the pet store has some data about all its animals, right? Let's say you have the hired by pet store to create a model that can identify a cat. So pet store has a lot of animals. They'll give you some data about one animal in particular, and then you have to, based on that data, identify whether that animal is a cat or not. So what sort of data will the pet store give you? So they have their database, which contains, for every animal, let's say its height, its width, its color, maybe diet, maybe age, and whatever, right? And your goal is to create a function that takes one animal's data and predicts 1 if it's a cat, and 0 if it's not a cat. So we have this, we want to make this function that does this. Where do we start?
From input? Inputs?
From the inputs, your intuition. We have a lot of these details about one animal in particular, right? Are all of these relevant? Do you need all of them to be able to make this decision?
Yes. The more the better.
The more the better.
But there's
Okay.
a point of like diminishing returns though.
There is a point of diminishing returns.
Right. I challenge that you don't necessarily need all. I'm just saying that. Depending on what he's looking for, I may not need all. For example, if it was a different scenario and I wanted teach them that you can go on a ride or not, and I know their age, height, blah blah blah, and you need their height. That's a really simplistic. That's too extreme. But I just challenge that I don't think you need all.
That's fair enough.
More the better.
Think about
is
it.
not the better.
If you have, does the height of an animal tell you anything about whether it's a cat or not? Could be. Sure. What about
It's a lion.
what?
Suppose it's a lion. That's a fact.
Yeah, suppose it's a lion, right? I'll say weight as a weight, right? Does the weight of an animal tell you anything about whether it's a cat or not?
Maybe.
You say no. You say maybe. Let's see. The color of an animal, it's orange, brown, whatever, right? A diet. I personally think a diet could tell you a decent amount, right? Whether it's like a grass-fed animal, whether it eats meat or whatever. Does the age of an animal tell you anything about whether it's a cat or not?
Sometimes.
How? Think about it.
Well, I mean, isn't the reason why we put weights to, show how important it is for...
Well, we haven't gotten to weights yet. But what I'm asking you is, does the age of any animal tell you anything about whether it's a cat or not?
Yes.
Yes, it does.
Yes.
Oh no.
Cats and dogs have
Cats,
completely
yeah.
different
And
lifespans.
like extreme.
They have completely different lifespans.
Yeah.
But if you have an animal with the age of 2,
Yes.
it doesn't make sense. Dog can
Yeah.
be 2,
But if you have an
cat can be
animal
2.
age
We
like
don't know
30,
which one.
Yes, it can't be
Let's
right.
not be like a tortoise.
So
Right.
are we comparing all animals? Or
Yes, so we have the pet store will give you any animal at random. And for every animal they give you, you will have this information.
So I think age could tell.
Age is good, sure. What else? Which one is relevant to us?
I don't think colors is relevant.
I would say that we don't need to consider them separately.
We don't need to consider them separately.
Like there is no
The combination of them.
picking one and
Exactly.
try to give prediction by only one dimension.
Yes. So how do we make this decision? Let's say the pet store is very thorough in their database and stores 50 different what we call properties or features of any animal that they have, right? When the animal was adopted or when the animal came into the pet store, right? That is another thing that they would store. Does that tell you anything about the animal itself? Probably not. Right? The fact that I adopt an animal today doesn't tell me anything about
What the animal is.
what the animal is, right?
Okay, there's a case where actually it does.
Well, there's a case where
But
it
it's
does.
rare.
Yes.
No, that's what he's saying.
Yes.
Completely right, yeah.
Right? So how do we make this decision? And the first part is visualization or interpreting your data. One of the ways you could do this in fancy terms is using a correlation matrix, right? Write this down. That's upward back.
In my bag has fresh ones. Use mine. Use these. Not the ones in there. These one. Keep them. Correlation matrix. Exceedingly important. No, nobody here did research for us.
Correlation matrix, which essentially just means take all your inputs and plot them against each other and see if you can identify some sort of relationship between them, right? And usually the correlation matrix will give you these numerical values that tell you whether, like, how influential a particular thing is as compared to something else, right? And you don't need to train a network for that. You can gather those insights off of these like very, very primitive features directly off of that correlation matrix just by plotting it. If you see a straight line, they're probably related to each other, right? And that's one of the things. Now, let's make a model out of it. Let's say we select some subset of all of these features. This is what we call a label of our data set, right? So the information that we're given are features and labels. And we have to identify the relationship between these features and labels, right? So what do? Last week, we saw this idea of a neuron or a perceptron or whatever you want to call it that takes in some inputs and and computes their weighted sum. W1 all the way down to Wn. And by x, I mean our features, right? W is the relationship that these features are, their weighted sum. And we get an output. Instead of y hat, I'll just say y prime. Right? A prediction. So we take our inputs, compute some relationship, add them all together, and we get a prediction. So x in this case are our features, and y in this case is not our label just yet. Because the weighted sum exists between the space of all like real numbers. Right? It can be between negative infinity and positive infinity. But our output, we want it to be clamped between 0 and 1. How do we do that? Sigmoid. What is sigmoid?
It's a non-linear graph from 0 to 1.
Non-linear graph from 0 to 1. Oh, so
Activation function.
it's an activation function. Exactly. So another addition to our vocabulary are activations, particularly sigmoid. So before we compute our y, we take this weighted sum and pass it to this non-linear activation function, sigmoid. And that will take all values between negative infinity and plus infinity and clamp them between 0 and 1. And that can be then interpreted as a probability. How likely is it that given an input, it's a cat? Right? Now what do we do? Based on this, what we'll do is get a prediction, right? This is our model. We have a predicted value, and for every sample that we train on, we will have an actual truth value, right? And based on the difference between the predicted and the true value, we can evaluate the performance of our model, right? So we compute our loss, right? To evaluate the performance. What is our loss in this case?
The difference between like the true value and the computed value?
The difference between the true value and the computed value. Okay. True. Right. That's what? Doesn't really make a difference. Is this a valid loss?
Is it an error?
Hmm?
Error?
Error?
Yeah.
What do you mean?
Well, I know people usually use error like.
Error is just a term. So loss, error, cost, these are terms you'll be seeing interchangeably. Usually loss is defined for like one sample and cost is like for a batch of samples. Is there a problem with this specifically? Let's think about last week we saw mean squared error, right? We saw this difference and then we squared it so that our loss was always positive, right? But that was a regression problem.
I mean, like, there's a problem with loss because
It
it potentially could be negative.
potentially could be negative, right? So we square it so that
There
it's
is a span between 0 and 1, which
yes,
you need to be inside it.
exactly, right? This was the squared error that we saw last week, but that was for regression problems. Yeah. Regression problems are when we take a line and we try and like fit a curve through it, right? Is this a regression problem?
No. It was a classification problem.
It's a classification problem.
Binary
A
classification.
binary classification problem specifically, right? Because we have only two possible class values, binary classification, right?
This is special because binary classification problem require usually multiple neurons for all of the class, but since only two, you use one neurons and then clamp it to 0, 1.
No.
Is it?
No. In this case, there are only two classes.
Yeah.
Whether it is a cat or it's not a cat. I'm not saying that it could be a dog.
Yeah.
Right? That's why we only need one neuron. It's still a binary classification, but the classes are cat or not a cat. If the problem was cat or dog, then I can't use this, and we'll get to that eventually when we add more complexity.
I see.
Right? What we see is this is not valid or well, you can use this, but it won't give you that great results for binary classification problems. What we instead use is something called, and this was a term that they don't explain at all in the machine learning classes. What we use in this case.
This is recorded, by the way.
Yes, I know. Good.
Good.
It's called binary cross entropy.
Is this just log loss?
It is just log, yeah, binary cross entropy or log loss. I'll write this down as well. Binary classification, the loss is binary cross entropy, or the logistic loss. Right? What does that look like? It's a scary looking term, and the actual equation for it looks kind of freaky as well. But when you make sense of it, it's quite simple. You take the negative logistic loss, so y true log with y pred, and then I believe it's plus 1 minus y true log 1 minus y pred. That's our binary cross entropy. The actual true value multiplied with the log of the predicted value plus 1 minus the actual true value multiplied by the log of 1 minus the predicted value. Why are we doing this? It's like you can get, like this comes from a very, like you can derive this from a sort of probabilistic interpretation of neural networks or logistic regression. But there is an intuitive understanding as well. Think of all the possible values that can be for y true and y pred. Y true exists either 0 or 1, right? And y pred, when we clamp the values, is also either 0 or 1, or it can exist between 0 and 1, right? What is the log of 1? If we don't, it doesn't matter, it's 0, right? And the log of 0 is negative infinity, because the logarithmic curve looks something like this with 1, right? That's log, right? So if we just try different combinations of these, right? If let's say we're evaluating a sample that was actually a cat, this term will have some value, 1 times something, right? But this term, 1 minus 1, will go down to 0, right? In the other case, where we're evaluating a sample that was actually not a cat, well, this is 0, right? So this term evaluates down to 0. And this term is now evaluated and contributes to your loss, right? So you can break down this loss into your positive like class loss and your negative class loss, right? Just these two. Looks fancy. This is there's probably some like probabilistic explanation why it's called cross entropy loss, but this is what we use for binary classification problems, right? So this is our loss function. What do we? So we take a sample, pass it through it, get the loss, like whatever value it is. Now what? Now we are going to do another term which is gradient descent. Does anyone remember gradient descent? That's fine. We're going to go over it anyways. So, who here is familiar with the concept of derivatives? 1, 2, 3. Okay, cool. Oh, you guys as well. Okay. The essential idea, for those who are not familiar, is let's say we define a function y equal to x, right? As we increase x, so actually, I'll draw the code for this. Y equal to x looks like this at my graph, right? As we increase x, does the value of y increase or decrease? Increase, right? And as we decrease x, the value of y increase or decrease? Decrease, right? So the derivative of a function tells you what happens to the value of this, our function, as we change what it's dependent on. That's it. And if you take the sign of the derivative, that will tell you whether it's increasing or decreasing. That's the slope, right? So, in our case, what is our loss dependent on? Our loss is a function that is comprised of variables. What is the loss dependent on? Like what variables are here? That is y true
Y true and Y.
and y prime, right? We take y true to be some sort of constant that exists in the real world, right? It's a real world constant. Y pred is something that we change. Our model makes iterative predictions and we change it over and over again, right? So if we tweak the value of y pred, the value of loss will change, right? If we make it higher, the loss will either go up or down, and if we make it lower, the loss will go either up or down, right? So we can compute the derivative of the loss with respect to the predicted value, because this is directly dependent on this, right? Or this is directly dependent on this, right? And that will give you some value, right? What was y pred? Y pred was the output of the sigmoid of this function, right? So if our y pred is sigmoid of z, right, z being this linear part, well, this is again a function that's dependent on some variable, right? If we increase z, y pred will go either up or down. If we decrease z, y pred will either go up or down, right? So then we can decompose this. We can take the derivative of y pred with respect to z, or actually sigmoid of z, right? Let's decompose this for this is again a function that's dependent on this variable, right? This linear part z is just the weighted sum of our inputs, right? So if we're talking about this weight in particular, if we change this weight, z will change, right? There's a direct dependence on this for this. So we can decompose it further. The derivative of the sigmoid of z can be directly correlated with the first weight. And now we have this relationship between our loss here and this weight here, right? And there's the chain rule. Another thing to look into if you're not familiar with calculus.
I would do it later. I think you would have lost some people already. I think I would have. But anyway, keep
Yeah.
going with the chain rule. We can talk about that one.
Yeah.
Yeah, don't forget he has to go further.
Yes. Okay. Oh, you done? Well, a little bit. I want to increase the complexity a little bit of this, right? So this gives us how the loss changes with respect to this variable, right? There's a direct relationship here. And then based on this, we can change the values appropriately. Let's increase the complexity a little bit. Now this is where the intuition comes in, right? Now let's say they don't give you all of this anymore. They don't give you a database of height, width, color, diet, or whatever. Let's extrapolate all of this into another example where the goal is, given an image of a cat, or given an image of anything, given an image, predict whether the image has a cat. If image has a cat, right? So now our inputs change. We no longer have all of these defining features of a cat. All we have is this image of a cat, or not a cat. right? What do we do? How do you approach this problem?
We pass it to our perceptron.
We pass this to our perceptron. Cool. What do we pass?
The pixel and
The pixels. Okay. So our image, let's say, is 20 pixels by 20 pixels, right? 20 by 20 image. That's our resolution. And let's say it's a color image, right? By 3 RGB.
Alright.
So images are represented, right? This is a very weird matrix of pixels, or P1, Pn, right? It's organized in this way, where every P is RGB, right? How do you pass this complex thing into this?
You generate set of all combinations
Set of all combinations of what?
of pixels.
Okay, how many do you think those will be?
A lot.
I mean 400.
Yeah, 400 times
Factorial, yeah.
3.
Yeah.
If you're talking about combinations of images,
Oh, yeah.
it's,
Factorial.
yeah,
400 factorial.
well, do the something.
Big number.
Right. How do you pass this complex, like 3-dimensional array into that?
You will have a pixel as a variable and color as a weight. Or maybe vice versa.
Pixel is a variable, color is a weight. Okay, weight or some colors are determined, right? They're constant of a given pixel. We want to learn the weight.
Yeah.
So one thing we can do is take this and flatten it. Right? You take this weird looking cube of numbers and you flatten it out. Where this is R1, G1, B1, all the way down to R, N, B, N, Gn. Right? Now we have each of these pixel values. And then we can do the same thing. Sigmoid, linear, sigmoid, predicted. Right? This works. And was it time?
No, it's fine.
Okay. This works. If you like implement this in code and train it on a couple of cats or whatever, or no cats, the model will be right about 4 out of 5 times, which is not that bad. Why do we need neural networks now? Is the sort of last thing I want to come into, except for backtalk maybe. The intuition behind neural networks is you take this image, which contained the cat here, and then you flatten it out. So now this pixel is spread across 3 values, and this edge is spread across like this entire array. There's a huge gap between them, right? So a lot of the information that made it a cat here is lost when you like flatten it out. That's sort of where neural networks come in. Let's increase the complexity a little bit more, where we still won't get to totally neural networks. But let's say instead of predicting if an image has a cat, now the pet store wants you to identify 3 different animals. Given an image, predict whether the image has a cat or a dog or an iguana. Right? Image has cat or dog or iguana. Right?
What is that?
Iguana. It's like a lizard thing. They have them in pet stores. Using the same fundamental principles, how do you approach this problem?
We get image, we flatten it.
You get an image. Okay, perfect. You flatten it. Excellent. And then
Pass it to our perception.
pass it to a perceptron. Cool. And then
Activation function.
activation function. And then you get
Output.
output. What is our output?
What's the goal?
The goal is given an image, predict whether it has a cat or a dog or an iguana.
So this our output? No.
So okay, the y can be either this or this or this, right?
Like the way I thought about it is like you have three functions.
You have three functions.
Yeah, each of them returns either if it's a cat or not, if it's a dog or not, if it's a iguana or not.
That's a good intuition. So we have one logistic regression here, and you're saying this returns cat or not, right?
Yeah.
And then we have another logistic regression function which returns another value that returns dog or not. And we have another logistic regression here which returns iguana or not. Or not. Right?
Yeah.
Works.
But it's quite a lot.
I mean, it's quite a lot. But it's still not that many. So let's think about it. If our image is 20 by 20 by 3, how many parameters in our network?
Well, 100.
1200.
Actually, no.
So let's think about, let's consider just the case of a cat, right? 20 by 20 by 3 image, pass into this. How many parameters? You're on the right track. Parameters are these weights, and we're saying every pixel is connected to every weight. You're off by 1.
Isn't 1200 by 3 and then because you have 3 things and then 1200, 1200, 1200 and then those plus 1, 1, 1, 1.
Yes. So in this case, for a single neuron, we will have
And then
n,
the last.
the number, plus 1, the bias.
Right.
Right? Linear equation wx plus b. The plus b is not lost when you do any of this. In this case, since you said we duplicated the function 3 times, well, this one has 1200 plus 1, this one has 1200 plus 1, this one has 1200 plus 1. So it's 3n plus 3. That's the total number of parameters in the network. That make sense?
Yeah.
Huh?
Okay, well, got 20 minutes left. If you gotta do your stuff.
20 minutes left. I'll get through quick. Okay. A couple of brain teasers. What does our loss look like? And actually, before our loss, what does our y look like? What data do we? So in the case of a simple cat, we just gave it 1 or 0, right? Whether it was a cat or not a cat. In this case, we've duplicated the function. What does our y look like? What do we give it? Like our input is like x comma y, right? For every x, we have a corresponding y. Now we know x is still the same; it's still an image, as you said. What is y? What do you think y looks like?
Any number between 0 and 1.
Any number between 0 and 1. How do you make the decision that a number between 0 and 1 is either a cat, either a dog, or either an iguana?
Whatever has less estimation between the prediction and true value. I mean, like
We haven't made any predictions yet. This is our input.
Maybe that's like it returns an array of probability.
An array of probabilities. Okay, that's on the right track. I'm asking about what we give to the model to compare. So here we're comparing a y2, right?
Yeah.
What do we give to the model to compare? You are right. The model eventually we'll see it return the array of probabilities. What do we give to the model?
A corresponding array.
A corresponding array,
Like
right?
0, 0, 1 or maybe something like that.
1 hot.
Yes, that's what encoding about 1 hot encodings, right? So if we have cat, dog, iguana, this can be either 0 or 1, this can be either 0 or 1, this can be either 0 or 1, and we evaluate it based on that, right? So our y's will look like 0, 1, 0 for a dog. It will look like 1, 0, 0 dog for a cat, right? And then based on that, we can make these evaluations because we're still comparing individually whether this index corresponds to this index and this index corresponds to that index, right? So now what we feed into the network sort of changes depending on the complexity of our problem. Does that make sense? Think about it for a little bit. Right? 5 more seconds to think about it, and then I give you an even more trickier problem, a trickier brain teaser, which is, now we've established what an input looks like. What do you think this looks like? Like we give it an input, the model gives us a corresponding probability value, which we like using sigma clumps like either 1 or 0 to make the prediction, right? What does our loss look like?
3 times bigger.
Good intuition. 3 times bigger. Let's just do this 3 times. Right? But since we duplicated the function 3 times, let's duplicate the loss 3 times.
Right.
Right? One loss for like a given class, another for a given class, another for a given class. Right? Make sense?
Yeah.
So if all of these were connected and we like sum over all the losses, so I can write it down. Intuitively speaking, if I change this weight that's going down to dog, or the output of a dog, do you think that changes the output of a cat or not?
No,
It shouldn't. What do you think? If we change an input going into this neuron that's predicting whether it's a dog or not, will that have an effect on this neuron and this neuron?
Yes.
Yes, why?
I mean, you're feeding the same input to 3 functions,
We're
right?
feeding the same input to the 3 functions, correct?
So it would affect the other functions since they're all working based on the same input.
You're kind of right that we're feeding the same input in, but these weights are disjoint, right? This set of weights only goes to this neuron, this set of weights only goes to this neuron, and this set of weights only goes to this neuron. They're not communicating with each other at all, right? As he said, we just duplicated the function 3 times. If I didn't put this all in like this stack here, and I just had 2 separate functions, like here, the parameters of this function would not affect the parameters of this function, right? Because they don't communicate at all. So the complexity of the loss still doesn't change since we just did it 3 times. If we like compute the derivative of this loss with respect to a given weight, only this will change because none of these are affected by it. Does that make sense? If you write this loss down with respect to like 1 for each weight, the loss for, or the contribution of this has no effect on this for a sigmoid activation. Does that make sense? Because we just have 3 separate logistic regressions. 2 more constraints. Sorry. Let's say we have a constraint that you can only have 1 animal per image. In this case, since these are all independent, there is nothing stopping the model from 1, 1, 0.
Out of time. So I can
Oh,
do
yeah,
it next time.
sorry.
Yeah, do it next time.
Sorry.
That's fine.
There's nothing stopping our model from predicting this, right? 1, 1, 0, because they're all independent from each other. It could be this neuron think that there is a cat and this neuron think that there is a dog. There's nothing, it could be our image is both a cat and a dog, right? What if we add a constraint that there can only be 1 animal per image? How would we change that?
I would extend it, this output,
Yeah.
and like the output, this array,
Yeah.
I would take only once and like do the same thing and try, and then I would compare like first, second, and whatever have bigger value, I would make it as 1 and the other as 0.
That could work. There is a simpler way of doing it, which is by changing our activation. Right now our activation exists independently on all the neurons. Let's change the activation so that there is some communication happening here, right? We'll call that softmax. So the idea is input goes in, 1 neuron, 1 neuron, 1 neuron, right? And they give you, before the activation, they give you a number between negative infinity and positive infinity, right? We pass each of those numbers to this special softmax function, and this will give you 3 numbers outputted, which is an array of the same shape, so the same number of outputs as the inputs, but now all the numbers are between 0 and 1, and they all sum up to 1.
I think there's a trick if you have a list of sigmoid result, all of them doesn't sum up to 1, right? And then if you take all of them divided by 3, that is just softmax.
Yeah.
Oh, okay.
Or
Kind of.
maybe
No.
divided by the sum of all of the 3.
Yes, divided by the sum of all of these. Softmax looks like e to the, I think, x something is over sum over e to the k, something like that.
Yeah.
Is softmax. Or negative, I don't know, something like that. So now you see that because of this sum, we are taking the influence of all of these into account for every prediction, right? So now they're related. And this will give you an array of numbers, like let's say it will transform 80, 47, and negative 4 into 0.9, 0.05, and then 0.05, something like that. Although it will be more like evenly spread out depending on the contribution of each of these, right? So all of them sum up to 1, and they're also between 0 and 1. And then we can take the maximum value, clamp it to 1, and take everything else, clamp it to 0. So now we have one output per image, right? So the architecture of your model changes depending on the complexity of your problem, what you're trying to solve. The more constraints you have, your activation changes, the number of neurons you have changes, whatever, right? This is still technically not a neural network, but it's getting very, very close, right? If our problem was that given an image, predict the age of the cat, right? Age is now not a value that falls into a bin, like cat, dog, or iguana, right? It can be between 0 and positive infinity, right? Or, well, 14, 15 for a cat. So that turns into a regression problem. Maybe you want to use a different activation for that, so that it doesn't clamp those values in, right?
It's a very important concept. I want to take some time.
Oh, okay.
So
Okay, sorry.
It's fine.
One last thing then is, why do we need neural networks? The idea was we take the individual pixel values, compute the relationship between those pixels, and then make a prediction based on that. But as we saw, it's very difficult to compute direct relationships at the pixel level and interpret what makes a cat, or what makes a dog, or what makes an iguana, right? Because the edges of the image, or the distance between the eyes, all of that is lost when you flatten it, right? So the idea behind neural network is, let's take a slightly different problem. I'm going to get rid of this. And let's take the problem of like house price prediction, right? Given some features about the, I'd say, given some features about houses in a particular district, compute the price of the house, right? So let's say you're given house price prediction, right? And let's say you're given features such as num bedrooms. Let's say you're given features such as zip code. Let's say you're given features such as square footage of a house and average income of the neighborhood, right? What we can do is, instead of having a single neuron like this, what would have been done before like all of these statistical models is you would probably take the square footage, or not the square footage, but the zip code and the average income of a house, right? And that would tell you maybe something about the kind of schools that exist in the neighborhood. Oh, sorry. As a human, or as someone who understands the fields of like real estate, the zip code, the neighborhood, and the average income of that neighborhood probably tells you something about the kind of schools that there are, right? Maybe. Maybe the number of bedrooms and the square footage gives you something about the family size, right? That's living in that particular house, right? Something along those lines. And then these features are probably slightly better at estimating the price of a house because they incorporate more nuance in them, right? Like apart from just taking these as direct relations to the price, we take some relationships between those features, make new features out of them, and get the price. And it's noted that you would get a better estimate of the price this way, right? In practice, it's very difficult to make, like all of these are just numbers, right? It's very difficult to make these accurate relationships as a human between those two numbers. Like how, if I give you the zip code and the average income, give me a number that accurately represents the number, like the school quality. That's very difficult to do. So what's done is you take all of those features and you pass them through a fully connected or dense layer. Dense, fully connected layer, where everything relates to every other thing one time. Right? Like this. And then based on, like we make educated guesses, and then we tweak these parameters, right? And we hope, as Sarvani says, we let it learn these relationships. And the reason why neural networks are so good is because a lot of times the features that it learns are things that people might miss. Because you've incorporated this sort of idea that everything can be connected to each other. If like number of beds has no influence on the school quality, this weight will be driven to 0 and it will have no influence, right? So we just let it learn those features depending on the data. And the more data you put in, the more accurate, the more data you put in and the depth of this network increases, the more features you will be able to accurately represent. That's the motivation behind neural networks. And what's seen is if you make the network deeper, it can sort of understand or represent more complex relationships. What are those relationships? It's extremely difficult to tell. In the case, it's very interesting to visualize in terms of images specifically, because, well, you see everyone, even the guy in the video said, the first couple of layers identify edges, right? Pixel level representations of the data. And then as you feed it through the network deeper and deeper, it will understand features like face of a cat, the eyes, what makes an eye, what like combination of edges makes an eye. If I give pixel values to you and I tell you to identify these relationships, that would be very difficult. So we just let it learn. All of this process remains the same. Every feature is passed into one neuron. You get a linear sum, or a weighted sum of all the inputs, right? And then you pass it through an activation, maybe linear, maybe not, if you don't want to, and then you feed it forward. A couple of key terms is if you have a neural network like this, right? And this is your input. This layer, or these are called layers, right? Layers. A layer is just a collection of neurons that do not communicate with each other. There's no communication between the weights going into this neuron and the weights going into this neuron, as we saw here, right? That's a layer. The first layer that receives your input is usually called the input layer, right? And the last layer that gives you a prediction is usually called the output layer, right? The thing in the middle, or all the things in the middle, are usually called hidden layers. Why hidden? Because the input is hidden from this layer, right? The inputs that this layer receives are abstracted by the layer before it. That's why we call it a hidden layer. But the sort of pass through the network of the input all the way to the output remains the same. You just compute the weighted sum for all of them. You get a separate set of inputs coming into this layer. Pass it through an activation. Get a separate sum of inputs coming into this, and then you get the price. Depending on the time we have, I don't know. I will leave you off with a brain teaser. Is this weight going into the input layer directly contributing to the output?
Not necessarily.
Not necessarily,
Yeah.
but it might be. Are any of these weights directly contributing to the output? Because the loss still remains the same. I got rid of the loss function, but the loss is still the true value minus the predicted value, right? And the predicted value is the output of this neuron, which is dependent on the inputs that are passed into it, which are the outputs of this neuron, right? Which are dependent on the inputs passed into it, which are the outputs of this neuron, and then so on. So if you trace the path from the prediction all the way back, you will see that this directly contributes to the output. And if there is a direct relation between the input and the output, you can compute how the output changes as you change this, directly by that chain rule. So the pass that goes from the input all the way to the output, this is the forward propagation, or the forward pass through a network. And when you take the loss and contribute how each input or each weight like manipulates the loss, that is the backward pass through a network, or back propagation. The idea is still the same. Get the true value, subtract from the predicted value. The predicted is dependent on the sigmoid or the activation. Activation dependent on linear, and linear is directly dependent on the weights. It is just heavily abstracted in all of these connections. That's about it. That's intro to neural networks. Your marker. Went a little overboard, sorry.
That's fine.
Oh, no, that's good. All right. So, we need to break this down in digestible pieces. All right. But yeah, it's a good run through. So, what you could capture, you capture. We break this down piece by piece, and I have class now. All right. Okay.
I would highly recommend, depending on like whoever's interested, try writing the forward pass down, and then evaluating the backward pass. It's like an example of that would be. No, it's alright. It's alright. An example of that would be G of the first layer is the weights of the first layer multiplied by the inputs coming into it, plus some bias of the first layer, right? And then the activation of the first layer is just sigmoid of this linear sum, right? And then the output of the second layer, or the linear output of the second layer, is just the weighted sum of the second layer multiplied by its inputs, which are the activation of the first layer, right? Second layer receives an input, which is the output of this layer, plus some bias of the second layer, right? And then, and then so on. And at the end, you will get to the output of the last layer, which is the activation of the last layer. And you can directly trace the path back to any weight you want through this. That's why it helps to do this. You don't need to know the actual derivative value. Hope this was helpful. It is a lot of information.